Welcome to this module, and in this one we will look at the instrumentation amplifier. So, if you remember in the last modules what we have seen? We have seen the differential amplifier, and the differential amplifier was used to understand the how the difference of the voltages that we can apply can be used, and we can amplify the signal of the difference voltage. But what if I have to remove the loading effect, or what if I want to apply the sensor in terms of Wheatstone bridge and see the signal at the output. So let us rather than confusing you, let us see the circuit and let us understand what exactly instrumentation amplifier is, and let us go one by one so that you can understand how we can make a differential amplifier, or we can convert a differential amplifier to an instrumentation amplifier. Alright. So if we look at the circuit on the screen, what we see is that instrumentation amplifier is nothing but a closed loop device similar to differential amplifier, right. So, if you see what is this? This is a differential amplifier. Now, to this differential amplifier, but with carefully set gain and additional input buffers. So, what is this? You see, there is a voltage follower, this is voltage follower, but there is a resistors, there are resistors which are used to amplify the signal, which are used to amplify the signal. That means that this differential instrumentation amplifier can be fabricated or can be made by attaching or by integrating the differential amplifier with the buffers or with the non inverting amplifiers. Alright. So, its gain can be precisely set by single internal or external resistors. The addition of input buffer stage makes it easy to match the amplifier with the preceding stage. We already know this, right, what, that if I use voltage follower, then the loading would be negligible. That means that I can match the impedance with the previous stage to the differential amplifier if I use my voltage followers. Alright. This allows the instrument amplifier to be optimized for its roles as a signal conditioner of low level signals in large amount of noise. That means what? That if I have a small signal in presence of huge noise, small signal in presence of huge noise, then can I measure this signal in terms of can I extract this information even in presence of huge noise. So, let us do one quick experiment. By the time I will just read on the screen. If one of my TA, do you have a mobile? Find a YouTube where you see a screaming video, screaming, right, just find a video and then let me know. Okay. So, you come back, that is fine. So, I will put I will show it to you guys that how exactly what I mean by extracting the small signal in presence of huge noise. Alright. So, the point is here that the instrumentation amplifier, let us quickly once again see the instrument amplifier is a closed loop device like differential amplifier, but we carefully set gain. One. Second, it can, the gain can be precisely set by a single internal external resistors. Third, the addition of input buffer stages makes it easy to match the amplifier with the preceding stages. And fourth, this allows, so because of this condition, this allows the instrumentation amplifier to be optimized for its role as signal conditioner of low level signals. You see, signal conditioners of low level signals in large amount of noise, right. So, the high common mode rejection makes the amplifier very useful in recovering the signals buried in large common mode effects and noise. Now, you all remember what is CMRR, common mode rejection ratio. We have already seen in the theory class. CMRR is nothing but differential gain by common mode gain, AD by ACM, right. So, if I want to understand my CMRR should be extremely high. If my CMRR is extremely high, that means my signal to noise ratio is extremely high, that means I can measure the small signal in presence of huge noise, right, presence of huge noise. So, what is saying that if I have a condition where I have a signal and there is a presence of huge noise, there is a presence of huge noise, how can I use the instrumentation amplifier. So, let me put a so you see this is screaming, is a noise, and I am speaking something else also along with this. So, you see when there was third time, right, a man was screaming, right. I got a YouTube video where there was a screaming. First you can see very clearly a screaming noise, second it was screaming noise, third time it was screaming, I was also speaking. So, that screaming you consider as a noise, and my whatever I am speaking as a signal. Can you extract this signal by reducing the noise? Can you extract this signal by reducing the noise? If that is the case, then the instrument amplifier is extremely important circuit. Right, you got it. So, it is an example. So, if there is a crowd which is speaking in a one loud voice and suddenly one person is speaking in some other thing, you cannot hear in presence of loud noise. So, that is a small signal in presence of huge noise. Can you reduce the noise and increase the signal? Can you amplify the signal? If you use instrument amplifier, then you can do that particular thing, which is also written in this slide. This allows the instrument amplifier to optimize its role as signal conditioner of low level signals in large amount of noise, alright. You may not be able to understand very clearly in terms of maybe the sound, but if you understand this thing, that if there is a signal and if there is a noise, then it is easy to extract the signals from this noise or optimize these signals, right, with the help of instrumentation amplifier. Now, the high common mode rejection ratio makes this amplifier very useful in recovering small signals buried in large common mode effects and noise, alright. The output voltage is given by V out R4 by R3. So, if you see this particular circuit, right, V out is nothing but, you see differential amplifier you consider only this part, alright, only this part. What was V out? V out was R4 by R3 into V2 minus V1, correct. So, this was the one. So, you see here V out R4, let me just remove it, V out R4 by R3, V2 by V1, right. Now, what for this one, what is the role of this R2 and R1? If I connect in this particular fashion, I have gain 1 plus 2 times R2 by R1. This gain comes from the voltage follower circuit in this particular fashion. But you will also see circuits where you are neglecting R2 and R1. We will see, we will not have R2 and R1, it directly connect as a buffer, alright. And let us understand the instrument amplifier in terms of experimental approach, in terms of practical approach. So, if I see instrumentation amplifier in this particular case, what we have seen this particular circuit already, right. That means, here there is a Wheatstone bridge, you see there is a Wheatstone bridge, there is 1, 2, 3, 4 resistors, right, and the output of Wheatstone bridge is given to the buffer, and then it is connected to the differential amplifier, right. So, now you see if I do not connect buffer, then you know what will happen, loading effect will happen, right. So, I am connecting buffer to the differential amplifier, this makes my instrumentation amplifier. So, let us understand how we can use this circuit to understand the gain of the instrumentation amplifier. The aim is to calculate the gain of an instrumentation amplifier. This is our aim for today. The first one is connect the circuit as shown in figure. We have to connect the circuit as shown in figure 12, right. So, one is you understand only from here to here, alright. Another one is this circuit, which is your Wheatstone bridge, alright. So, connect the circuit as shown in figure 12, you just connect in terms of this one, apply 1 volt peak to peak sine wave to V1, 2 volts peak to peak sine wave to V2, observe the V out and note down the peak to peak voltage in the table below. So, we will measure V1, we will measure V2, we will measure V out, and from that we can measure the differential gain AV, alright. So, this is what we have to do, and then we can repeat the experiment for higher values and lower values. So, let us see how we can do this particular experiment on the circuit board and by applying 2 voltages at the inputs of the differential instrumentation amplifier. Like I said, instrument amplifier is nothing but buffer connected or integrated with your differential amplifier, alright. So, let us apply the input voltages to the instrumentation amplifier. Now, we have already applied the bias voltage to the operation amplifier, and now what we are looking at is we will apply the voltage V1 and voltage V2 to the instrumentation amplifier. Before we apply voltage V1 and V2 to the instrumentation amplifier, we have to adjust this voltage in the function generator. So, Sitaram is already working on the circuit. Like you see, this circuit was not prepared earlier, right. In front of you only he is trying to connect the circuit. So, if he can do in 1 or 2 minutes, right, you guys can also do in at least 15 to 20 minutes. So, it is very easy, that is what I am pointing out. It does not require really a premeditated things which will take lot of time or consume lot of time, alright. Once you understand, it is very easy. So, what he has shown is a Wheatstone bridge which are 4 resistors. If you can focus here on these resistors, please. Yes, these resistors. So, these are the resistors which he is showing, which are 4 resistors, right. You can see here 4 resistors. So, this is a Wheatstone bridge, and then instrumentation amplifier is somewhere differential amplifier. Can you please show differential amplifier? These are differential amplifier, right, and to this differential amplifier we are connecting buffers. Where are buffers? This is 1 and this is 2, alright. There are 2 buffers, 1, 2, differential amplifier is here and Wheatstone bridge is here, right. Now, let us apply first voltage to the differential amplifier. So, we will apply 2 voltages, right, V1 and V2. If you come back to the circuit, on the slide, yes, what we are applying right now, we are applying voltage here and voltage here, alright, V1 and V2. So, let us go back to the breadboard, alright. You can apply 1 volts and 2 volts respectively. Alright. So, what you see is function generator, you can see there is a 1 volt, there is 2 volt, frequency we have set at 1 kilohertz, phase is 0, offset is 0, and now we are connecting again to check whether it is 1 volt or 2 volt with the oscilloscope. As you can see, right, ground with ground, phase with phase, or signal with signal, and then we have to understand whether it is correct or not, and we see it is okay. Now, he can apply it to the input. So, he is applying to the input here, if you can see on the breadboard. Right. So, he has applied the signal to the input of the differential of the instrumentation amplifier, alright. Now, when he applies input, we have to check the output. That is what we have to do in the experiment. We have to apply the input. Okay. So, this is only one input he has applied. Now, he is checking the second input again with oscilloscope. So, you can see in the oscilloscope, yes, and you can, if you focus, it is around 2 volts peak to peak, right, 2 volts peak to peak. Okay. Now, again you go back to breadboard, please, and he is connecting the second input, to the instrumentation amplifier, ground to ground. Now, we have applied voltage V1 and voltage V2, right, and we will measure the voltage at the output. We have applied voltage V1, we have applied voltage V2. Now, we are measuring the output of the instrumentation amplifier, alright. So, this is in this configuration. You understand, neglect this Wheatstone bridge for now, just understand the voltage directly applied in the buffer V1 V2, output voltage V out. So, we are measuring V out, V1, if you see here, what is V1? 1 volt, V2 2 volts, V out we have to measure. From that we will say V out 2 minus 1 is 1, right, and what is V out, let us see what is V out. So, if you see again the circuit, you will see that he has connected the output of the instrumentation amplifier to the oscilloscope. So, if you see the oscilloscope, you will see the result, and if you see the output is 1.04 volts, output is 1.04 volts, right. So, let us write down output on the screen. We will write output as 1.04 volts. So, I write 1.04 divided by 2 minus 1 or 1 minus 2, this is equal to 1.04. So, my gain that I have calculated is nothing but 1.04, alright. So, this is how you can use the instrumentation amplifier with buffer, right. Now, what will happen if I directly connect the potential divider output and see what is the voltage difference between V1 and V2. So, if I measure voltage here, and then what I will do, first I will measure voltage here, and then second I will measure voltage at V out, alright. So, first I am measuring the voltage at the output of the Wheatstone bridge or the output of the Wheatstone bridge. So, I have to apply voltage across the Wheatstone bridge, and if the Wheatstone bridge is properly tuned, then my output voltage would be 0, right, output voltage would be 0. So, if you see again what he is trying to connect, he is trying to connect the Wheatstone bridge with the supply voltage, and we should expect the output to be 0 volts. So, he is applying a supply voltage across the Wheatstone bridge, and the voltage is, you can see here, voltage is about 5 volts, okay, and then he has to measure the voltage at the output of the Wheatstone bridge, and the voltage should be close to 0. So, let us see, he is measuring the output voltage, and you can see the voltage is close to 5.4 millivolts, right, 5.4 millivolts. Now, if this voltage he applies to the buffer 5.4 millivolts across the buffer, 2 buffers, and he is measuring the output, final output at the output of the instrumentation amplifier, then what we are able to find out, the output of the instrumentation amplifier is, you can see what is it, 42.6 millivolts, right. So, there is a difference, isn't it, there is a difference, and that difference, why there is a difference, find it out. Always and not give you all the answers to all the things that we are doing, you try to find it out by yourself, why there is a difference when we measure the value here, why there was a difference when we measure the value at the output of the Wheatstone bridge, alright. That is your kind of homework, right. I do not like to give homework because I do not believe in homeworks, I believe in actual thing, and I believe that student will do homework if they really want to study, right. You cannot be forced to attend a lecture, you cannot be forced to do the homework, you cannot be forced to do the assignments, you should do it by yourself, right. It is your will, your zeal to learn. If you do it, you will learn more. If you do not do it, it is okay, you know. So, what is the circuit here? What is the circuit? You see, connect the circuit as shown in figure. When we have completed experiment, let us clearly see what we have done. Here R2 is short circuit, R1 is infinite or open circuit, right. This we have considered. Why? Because if you see earlier part here, right, here what we have seen, here we have R2, R1, right, here we have R2 and we have R1, and this R2 and R1 was having an effect on the overall voltage V out, correct. Now, in the experiment what we have done, we have considered as R1 equals to infinite or open circuit and R2 short circuit, correct. So, you see here there is no R1 and R2 here, can you find R1 and R2? There is no R1 and R2, right. Now, apply 1 volt peak to peak sine wave at 1 kilohertz V1, 2 volts peak to peak sine wave at 1 kilohertz V2. So, apply one V1 here, V2 here, observe V out and note down the peak to peak voltage. We have done that experiment, repeat the experiment for higher and lower amplitudes and note down the observation. So, we have not seen higher and lower amplitude, but we have actually seen the voltage when we applied directly to the input V1 and V2, and we have seen that when it is connected through the potential divider or Wheatstone bridge, what is the V out, right, this we have seen. So, let us quickly see if we change the voltage, that means that if we lower the amplitude, lower the voltage, what will happen. So, right now what we applied? We applied 1 volt at the V1, 2 volts at V2. Now, let us apply 0.5 volts at V1 and 1 volt at V2, right. So, you see in function generator he is right now applying 0.5 volts in channel 1 and 1 volt in channel 2. What will happen if I apply 0.5 volt in channel 1 and 1 volt in channel 2? What do you expect? What will happen? V out, what will be V out? So, I am applying directly V1 and V2 to the buffer, alright, applying directly V1 and V2 to the buffer. Again he has to he is checking which one is channel 1, which one is channel 2, not exactly, is he doing that? No. What he is checking? He is checking the signal in the oscilloscope to confirm that there is 1 volt peak to peak and there is 0.5 volts peak to peak. So, once he confirms his experiment, you can see the oscilloscope please. Yes. So, he can see 0.5 volts from channel 2. Okay. Alright, 0.5 volts in channel 1, 0.5 volts in channel 1, and then he has to also see 1 volts in channel 2. So, let us first connect channel 1 to V1, channel 1 to V1. All right, and now he has to check 1 volts in channel 2, 1 volts that we are applying to channel 2. So, again he will take a probe from function generator, which he is right now doing, and he is connecting the probe to the oscilloscope to again check whether it is 1 volt peak to peak. He has to check whether the function generator he has applied 1 volt, is it 1 volt or not, he has to check it on the oscilloscope. So, if you see it is 1.04 volt peak to peak, alright, peak to peak. Okay. Now, he will apply this signal to the V2, to V2. So, he is applying it to V2, as you can see. So, you have to make sure that the ground is connected with the ground and signal to the signal, and when you applied V1 and V2, what is output? Output you have to connect to the output of the instrumentation amplifier and measure the signal in the oscilloscope. So, you see when he connects it, you can see the signal in the oscilloscope. The output is, if you focus on the oscilloscope, you will see 540 millivolts, 540 millivolts. So, earlier when we were looking at the output was close to 1.04 volts, here it is 540 millivolts or 0.54 volts, right. So, what will be the output? What was expected? Output was expected or 0.5, because the gain here we have kept as 1, right, the gain is 1. So, if gain is 1, that means that my output V out, let us see, 0.54 divided by 1 minus 0.5, which is nothing but 0.54 yeah, divide by, sorry, divide by 0.5, correct. So, 0.54 divided by 1 minus 0.5 or 0.54 divided by 0.5, this is close to 1, this is close to 1. So, this is how you can measure the gain of the instrumentation amplifier. Very important experiment, very important circuit. You have to understand instrumentation amplifier because it is used in large number of circuits, alright. So, understand this. Now, let us see the part 2 of the instrumentation amplifier, which is the last circuit for this particular module, and here we have to again calculate the gain of an instrumentation amplifier, but here if you see there is a slight change that we have made. What is the slight change? The slight change is here we have considered the same circuit which we have used to understand the theory, right, which is that you have here R1, have here R1, you have your R1, and instead of R2 you have your RG, you have your RG. So, what is the formula? If you remember, the formula would be V out equals to, here you see here, right. So, here is nothing but R3 by R2, right, into what is this one, this formula for this one you have seen, right, 1 plus 2 times R1 by RG into V2 minus V1, correct. So, this is the formula that comes into effect if we are going to use this circuit, if we are going to use this circuit, alright. The advantage here is you can change the gain, you can change the gain by changing the pot. What is pot? Pot is potentiometer, alright, or variable resistor, right. If those, for those people who do not know how the potentiometer looks like, is in the next circuit, you will be able to see how potentiometer looks like. Like I said, do not feel that, and the beauty of this NPTEL is that you really do not have to feel embarrassed, right. There is no person around you who can tell whether you know or not. If you have that mentality, first of all, I told you very clearly that lot of things we do not know, and if we are in class and if we ask, right, that means you are curious. It is not that you do not know and everybody knows. So, do not feel that when you ask a question that means you are the only guy or only girl in the class that does not know the answer or that do not understand the things, right. In fact, I take it in a different way. If my student asks me question, that means the student is curious, right, curious to understand, curious to learn the things. So, the point is for those people who do not know how a potentiometer looks like or how a variable resistor looks like, we will see in the next circuit soon, once I complete the this slide. So, what we have to do? We have to connect the circuit as shown in figure, alright, we have connected. Now what? Now what to do? So, now here resistors R2 and R1 have finite values, okay. R2 and R1 have finite values, R1 is 1 kilo ohm, R2 is 1 kilo ohm, okay. Apply 1 volts peak to peak sine wave at 1 kilohertz. So, actually you see we can also say, so R2 and R1, we also have here R2 and R3. R2 and R3 also has the same value. So, do not worry about finite values or not, do not really bother about this, right. Apply 1 volt peak to peak sine wave at 1 kilohertz to V1, 2 volts to V2, observe V out and note down the peak to peak values in table below. So, this is the same circuit if you remember, right. The only difference here is that we have now considered this particular resistors, set of resistors, and that is why the formula is little bit changed. Calculate the gain observed in table and compare with the theoretical gain. So, let us see if I apply voltage between between the to one of the buffer, voltage 1 to buffer 1, voltage 2 to buffer 2, buffer is nothing but voltage follower, what will be the output V out, alright. So, let us see, again you can see, so please disconnect the breadboard. You see if you can look at the breadboard, now he is disconnecting the previous circuit, which in which we have used buffer without the R2 and R1 or RG and R1, alright. There was no feedback if you have seen. okay, and now he is bringing a circuit. It is similar circuit except that there is R1 and Rg. So, can you see, and for those people who do not know, right, I told you this is the potentiometer, alright, this is the potentiometer, it is called pot, POT pot, and the value here is written 100 K. If you can see, I do not know whether you can see or not. Yeah, 100 K, right. So, this is a 100 K pot, there are 3 terminals in the potentiometer, here 3 terminals are there, right, and you can use the 2 terminals, and the third terminal you can ground it, or 2 terminals you can short and 1 terminal you can use it. If you go to YouTube and see how the pot can be operated, you will be able to see. It looks like this. You can, if you change this knob, the resistance value changes. All right. If I change this knob, the resistance value changes. I can use it clockwise and anti-clockwise. Don't try to go beyond its capacity. So once it is moved, no equipment requires too much of force, brutal force. This is all electronic equipment. There is no mechanical. This is not a workshop. So, do not apply extra brutal force to any electronic equipment, right. You have to turn it clockwise, you have to turn it anti-clockwise to change the resistance. Now, what he is doing, he is trying to measure the resistance of the potentiometer, and you can see the resistance here on the multimeter. You see, you can change it for 419 kilo ohms, 62 kilo ohms, 63.6 kilo ohms, 67. So, he is turning the knob and you can see the change in resistance, right. So, this is called a potentiometer, alright. Okay. Anyway, so let us now adjust the value of the potentiometer and apply the voltage V1 and V2, which we have already set in the function generator, which we have already set in the function generator to the instrumentation amplifier, amplifier. Again, understand that whenever you want to measure the resistance of the potentiometer, it cannot be connected to the circuit. You need to disconnect the potentiometer, because then other parameters will come into effect and you will not get the actual resistance, alright. So, whenever you want to measure a potentiometer, please disconnect it from the circuit. If you see now, he has disconnected it from the circuit. I thought earlier that it was disconnected, but now he has disconnected. So, you can see now change in the resistance values, right. If he sees, it is changing 2.2, 2.4, 2. Because how it can be more than 100 when the maximum maximum kilo ohm or maximum range is up to 100 kilo ohms, it cannot exceed 100 kilo ohms, right. So, we are connecting now potentiometer as shown in the circuit, if you see the circuit on the screen, he is connecting the potentiometer as shown in the circuit. And he is also connecting resistors R1 like you see in the circuit, and then he has already prepared, this time he has prepared, alright, this particular circuit which is here, right. So, what he is trying is just trying to connect the potentiometer as you see on the circuit. Now, he has already connected, now he will apply the signal voltage. He has already we have seen in the previous experiment 1 volts, and now you can see here the signal from the channel 1 is 1 volt peak to peak is channel 1. Yeah, and now connect to channel 2 please. And let us see both the channels together. Yes. So, channel 2 apply some different voltage. Okay. So, you can see channel 1 is 1 volt, channel 2 is 2 volts. This is we are applying to the instrumentation amplifier at the input. Can you please connect it? One volt at one input, 2 volts at another input, and now we are trying to measure the output, alright. We are trying to measure the output of the instrumentation amplifier. We can measure the output by connecting the output of the instrument amplifier to the oscilloscope, When we try to do that, then let us see what is the output. Do not forget to apply the bias voltage to the operational amplifier circuits. So, we have to apply plus 15 minus 15, right. Okay. Ground to ground, alright. Turn on the DC power supply, yes, plus 15 minus 15 is given. Now, he is connecting the output of the instrumentation amplifier with the oscilloscope, and once he connects it, we can see the output of the instrumentation amplifier on the oscilloscope, alright. So, ground he needs to connect it. Okay. Can you just alright. So, what is that, what we see? Minus 13.4 volts, is the output of this particular instrumentation amplifier, right. So, again I said it depends on the feedback resistors, it depends on the 1 plus 2 R 1 by R g. So, when you put all the values together, you will find that the output voltage would be close to what we got in the experiments, and you can also understand that we can change the gain, because here the gain is extremely high. Why? Because we have changed the potentiometer. You see here potentiometer, the gain is extremely high, and that is why you can see that the output is minus 13.4, which is very close to your biasing voltage. If we reduce the gain, so can we reduce the gain and see if there is a change? So, what will happen if we reduce the gain? If we reduce the gain, then we will be able to see the change in the voltage, but for now it is fine, do not worry about it. For now let us just understand that if you use the differential amplifier in this particular configuration along with the buffer, it makes the instrumentation amplifier. So, if you use differential amplifier with buffer, makes instrumentation amplifier. If you use this particular circuit, then it will help to have different gain, you can change the gain. If you have the previous circuit, here you do not have any control on changing the gain except value of R3 and R4. The role of this buffer is to reduce the loading. The role of this buffer is to reduce the loading effect. So, now what we understood is that when we use an instrumentation amplifier, right, it is nothing but a combination of your differential amplifier and your voltage follower or voltage buffer. So, from this set of experiments, let us see the final slide. And final slide today is another quote from Dean Kamen, which he says that every once in while a new technology, an own problem and a big idea turn into an innovation. You see once in while, generally when we do research, right, it is called researching the things which already searched. So, but while doing a research, while we are trying to understand the problem and we dig into the problem, we can find old problems and we can understand whether we can find a solution to this problem. Sometimes this finding solution of the existing problems will result in a innovation, right. So, always try to see the problems around you, along with, like I said, I strongly believe that when you learn electronics, excellent, when you learn any other subject, excellent, but try to see and be kind to other people, be kind to other humans, fellow humans, because I believe that that you can be a good scientist, but if you are not good human, it is not useful, right. So, be a good human, and if you are good human, you can be an excellent scientist, you can be an excellent engineer. So, with that particular quote of Dean Kamen, what why I think is, let us recall quickly in this particular module, which is the instrumentation amplifier. Here we have used nothing but a differential amplifier, we have used a buffer, then we have seen a Wheatstone bridge. So, Wheatstone bridge, buffer, instrument differential amplifier together, or except Wheatstone bridge becomes your instrumentation amplifier, alright. And then we can change the gain of the instrumentation amplifier by changing the value of Rg, which is a potentiometer. Potentiometer you guys have seen. If you do not understand, I will just take it out from the supply, which is here, and if you can just switch it off and take it out please, potentiometer, so that we can quickly see once again. Yeah. So, yes. So, if you see in my hand, this is a potentiometer, this is a potentiometer in my hand, right, and what we can do is we can change it, we can change, we see I am twisting it, right, you can, and this is maximum. I will not force more than this, alright. See, slowly I am turning it until it reaches to a one point. Beyond this point I cannot turn it, I should not turn it, right, I cannot and I should not, alright. This is the potentiometer, clockwise, anti-clockwise, clockwise, anti-clockwise. There are 3 terminals here, you can see here, right, and you can use potentiometer to change the resistance from 0 to 100 kilo ohm. 0 again is the ideal value. So, extremely low to 100 kilo ohm, that depends on the type of potentiometer you get. The one that I have is about 100 kilo ohms, right. So, using the potentiometer you can change the voltage, you can change the gain of the instrumentation amplifier, alright. So, in next class, in next modules, we will see other application of operational amplifier. Till then you kind of keep understanding, keep reading the lectures notes, keep understanding or reading the theory that we have studied, because most of the things that I am teaching now in this particular classes are related to theory classes, alright. So, try to keep yourself up to date by reading the things which you have already studied in this particular course. With that, you take care, and I will see you in next module. Thank you.